Hello and welcome to another video on analog and digital music. Here we're looking at the oscillator of a synthesizers.com rig. And as you can see, we have a 1 volt per octave input. This input raises the basic pitch of the oscillator so that we can play across the scale. Now, all analog oscillators have a calibration and a certain tracking error. That means that there's a few millivolts difference between what the tone should be and what it actually is. This normally may not cause a problem if you're just playing with one oscillator. But if you have 2 or more oscillators in a patch, it's pretty difficult to get them to track identically across the entire keyboard. And this produces some of the effects associated with analog gear which is not present in digital gear. Oscillators in analog gear are free running. That means they're continuously oscillating, and as a result, since there's no synchronization as a rule between the two of them, there's a random phase change that goes on as the two waves slide in and out of phase. Nothing like this happens in a digital keyboard. When you press a key, all the frequencies of the various tones start in exactly the same cycle, so there's no phase shift unless it's deliberately introduced between the notes. So not only across octaves is there perfect tuning, but even between notes. So what you want to do is hear the effect and see the effect on an oscilloscope, and also you want to observe the hard sync, which you can see there as an input. Even though this allows us to synchronize the two oscillators, it doesn't bring us anywhere near to the precision of a digital system. As an example of what we've been saying, we're measuring the pitch output of one of our MIDI interfaces. It should be reading 0, but notice that the voltmeter is actually reading 0.6 millivolts, which is negligible. When I touch the octave button, that is when I play a note an octave up, I just touch this octave button. But notice that it's actually reading 0.997, which in this case is negligible. Now I've put the pitch output into a multiple, and the multiple allows me to send that one voltage to 2 different places via those 2 orange cables. So we send it to the 1 volt per octave input, the tracking input of 2 oscillators. And we've got the sine wave output of the 2 oscillators coming via the yellow cables and going into a 4-channel mixer. Here we're only using 2 of the channels, and then out to our amplifier via that black cable. Now the waves are tuned pretty closely, and you might be able to hear them sliding in and out of phase. Or rather, it just gets louder and softer. That's the phase shift which we're talking about. You can hear the waves there sliding in and out of phase as they get weaker and louder, softer and louder as the phase shifts between them, and we'll show you that on the oscilloscope. Okay, the waveform frequencies are very close, and as you can see, they're temporarily holding in that phase arrangement. but eventually they're going to slip and slide. You can see now that they're moving more in phase, and you can hear that it's getting a little louder. Because this is so excellent, this synthesizers.com rig, the oscillators are very stable, but it's pretty impossible to stop the sliding with time. As you can see, it's about to go out of phase there, and it's going to decrease once the two of them are out of phase. That means the top hump on the bottom one coincides with the bottom hump on the top one. And notice that the amplitude of the tone has completely decreased. To enhance the phasing effect, I'm going to slightly detune the top one. There you can see now the top one is sliding relative to the bottom one. The phase is changing, and you should be able to hear it in the sound as it gradually increases and decreases. The amplitude is minimum there. The amplitude is maximum there. The amplitude is minimum now because they're out of phase, and the amplitude is maximum there because they're in phase. If I add the two waveforms on the oscilloscope, you will see what's happening. Maximum amplitude, minimum amplitude, phase reversal. Maximum amplitude, minimum amplitude, and phase reversal. Now if I want to get rid of this effect, I can plug the hard sync into the pulse output here, and now they're permanently phase locked. Observe that the phase lock is they're not sliding anymore. We've got a perfect phase lock on both of the waveforms. I cannot stress enough that this random phase shifting is entirely a function of analog equipment. There is no counterpart to this in digital at all. Digital oscillators are always in sync. They're not free running like this, and they're not prone to shifts and changes in frequency as happens with analog components. Now hear the effect as we go up the octaves and the tracking error increases. Here we tune them at the low frequency so they sound like they're in perfect tune. We go up an octave and they're still pretty good. We go up another octave and we can hear them beating there slightly, but it really comes home to roost when we go up another octave. There you can hear it warbling. Can't you hear it warbling? And when we go up one more octave, now we can really hear it singing. And if you're not really sure that you hear it, I'll bring these into tune now. Listen carefully to that. Now as I go and I tune it, hear it? Can you hear it? The problem is if I tune it there and I now go back down to my lowest octave, they're beating down there. Remember, they were formerly tuned down there. So in fact, there's absolutely no tuning at all that I can do that will give perfect tuning across the entire keyboard. And this is only with 2 oscillators. The situation is magnified if I have several more oscillators all tuned to harmonically related frequencies. Now you might think this is a terrible thing now and you want to get back to your perfect digital world. But in reality, just turn that off so you can hear me talk. In reality, actual acoustic instruments in an orchestra are in the same boat, because they're not digital either. Every violin has to be tuned by hand, and it's not perfect. So as you move up the scale of the violin, there's going to be various errors introduced. Just think of your own guitar, and if you check your guitar with a tuner, you may tune all the strings perfectly in the open position, but when you press it on a fret higher up, say the 12th fret that gives you an octave, do you get perfect tuning up there? If the guitar neck is properly adjusted, it should be pretty good. But you cannot completely eliminate these analog errors on all strings all down the neck. Even with an expensive guitar, you're going to get a few cents difference across the fretboard. So what I'm trying to say to you is that the analog synthesizer perfectly matches the instruments that the human race was accustomed to until the age of digital. Digital introduced a perfection that was not possible in anything analog. Thank you for watching the Stephen Mendes channel, and we'll continue the discussion in another video.